Okay, students, so we have started our live stream. Fine. So live stream is also started and now there's no any problem. So now we can start our class. And okay. So where we were at the in the last class, let me see this. Okay. So here we go. So students, please be very much focused on the slides here. Okay. Be very much focused on the slides. So let me see how many students have joined. Sneha, welcome to today's class. JNV Malhar students, welcome to today's class. Okay. So be very much focused. Okay, let us start it now without wasting any time. Okay, you have texted in the chat. Good afternoon. Yeah, good afternoon, everyone. Okay, good afternoon. See, where we were at the end of the class yesterday. So it's a Bhopal region. So according to that, yeah, we started for refraction from a prism, isn't it? I mean, we left at this point. So you both can text in the chat box, students, and it will be good. Otherwise, class will be like, it feels class is like boring always, because if you're not responding, what's the use? So let me tell you here one thing. This is reflection from prism. Okay. After we'll see dispersion of light by prism. Okay. So I think we were at one of the numerical in the previous class. Okay. We were at one of the numerical in the previous class. So that we'll see here. Fine. So if we see it pause, okay. So I'm audible, no, properly. Okay, if you want, I will launch this. Please participate in this. Click yes or no according to the questions here. Okay. So one of the students have participated. Remaining two students, I want to participate in this. Very good, very good. See, main thing is what slides. So that must be visible properly and audio must be clear. And that is all about. Okay. That is all about. Okay, so now I'll be ending this. So I'm audible, it's fine. Let me see the YouTube students, what they are doing. Okay. So what is happening on the YouTube? Let us see there. So this is YouTube students. Okay. Here also it's good. Take fine. Yes. So we are here. Okay. So we were at the numerical in the previous class. Then we'll see today dispersion of the light prism via an image and all. Okay. The rainbow formation and scattering of light. This we'll see. These were the all things, no? Is it fine, students? So I'll show you a slide. Tell me where to stop. Okay, so let us recall some more about this prism. So I told what? I told a white light will be coming. Okay, and prism will show dispersion of this white light into 7 colors. Say VIGYAN. Simple thing, not a lot. Then I told this thing that for understanding refraction, this is suppose a prism. So this was a glassy material inside. So it is having refractive index. You can call it as like 3 by 2, 1.5. Okay. And this was an apex angle or angle of the prism. If I can show you here, printed version is. So ray was coming like this and it was showing a refraction at the first surface like this, going from a rarer medium to a denser medium. Then again, refraction at this point when the normal is drawn somewhat like this, if you see it. Okay. And then it will emerge as an emergent ray. Okay. And that angle is mixed with the normal is emergent angle. So from now it is from the denser to the rarer medium. These all things we have seen. So ultimately we have derived one quantity for this, that is deviation angle, by using geometry. By considering this thing, angle A equals to 180 degree minus this angle. So all the geometry will be given to you. Ultimately we have derived angle of deviation, this formula. This also you must remember. Let me erase this thing. So ultimately we have derived this thing, that is angle of deviation here, students, is equals to incident angle, okay, emergent angle, this is what angle of prism. Okay, this complete is known as angle of deviation 1 plus I minus A. This is angle of deviation, students. Okay. Okay, one more student have joined. Jinvi, say Anshu have joined. Okay, cool. So this we have seen in the previous class. Then we have seen this graph that when a rays incident like this goes inside and deviates outside like this. So for two angles of incidence, say between 20 to 40 degree and 60 to 80 degree. Okay, I repeat it. For two angles of incidence shown here between 20 to 40 degree and between 60 to 80 degree. Okay, there is only a single angle of deviation here. This is known as, this is a single angle of deviation here. Okay, and also it was confirmed here that there will be some angle of incidence for which the property is this. I mean, this is the low there, emergence angle will be same, both of this. Also you'll find R1 here, that's R1 equals to R2 for this. I mean, for that it will be parallel to the base, and that conditions will be like this. If it's parallel to the base, then that angle of deviation will be minimum, and this, that angle of minimum deviation is shown on this graph like this. Suppose it is 40 degree for particular angle between 40 to 60 degree. Okay, so by using this we have made this angle of deviation minimum by using some certain geometrical things. Let us see it now. Okay, so let us derive it. So this thing, I mean, when the ray goes inside and goes inside this glass prism, so it will be parallel to the base and comes out like an emergent ray. Yeah, so we say here that this angle of deviation will be minimum angle of deviation, minimum angle of deviation okay, at the minimum angle of deviation we say this is equals to dm. I is equals to e here. Okay, so we know this thing that a refracted ray inside the prism becomes parallel to its base here, as you will know. So applying all this thing, ultimately, if I solve it fast, I mean, you'll see this on the PDF. The formula which is required for us for the application is what? It is this. That ultimately we got this formula, which gives you like this. This is a refractive index of the internal medium of the glass, I mean the prism, with respect to the external surroundings S. Okay. -1 into A is what? Angle of prism here. Fine. So we have derived this thing, so we got somewhere you'll find this angle of minimum deviation like this also, mu -1 into A, where A is the angle of prism and mu is the refractive index. But don't worry, okay, because the things are same, only the symbols are changed. What is changed? Only the symbols are changed. Okay, after this we you were ready for this concept question, and in the last class I've ended here. Is it was this, is this fine, students? So I told you to find the answer, right? So what was the answer? That angle of deviation was like this. See, this is, we know angle of deviation is n2 means what? N2 means refractive index of this with respect to the surrounding mediums. S S क्या है इसका refractive index क्या है surrounding medium का 1, इसका क्या है 1. So n2 1 will be what? It will be, or you can say like this simple. I must show it properly here. So we'll say that this n2 1 is basically nothing but n of internal glass upon n of s. It is 3 by 2 upon 1. So we'll put it here, this value -1 into angle of prism is 4 degree here. Okay, so this will be the value. That is angle of deviation comes out to be 2 degree. Okay, this is what? Angle of deviation. And that was asked in this question. Okay, students, now text me. Up to here you understood? Up to here you understood or not? Please reply in the chat box. Okay, very good, excellent. So who is this student? Sneha Ghosh. Sneha, excellent. Okay, all clear. Okay. So where we were at the end of the class? I mean, we have to start from this point. Okay, let us solve this question also. So this is also numerical. Okay. So in this numerical, what is the condition is this? This incident ray is going like this. You know, it is showing the minimum angle of deviation. You see, even by just looking the picture, you can say like this, that angle of deviation is minimum. How can you say, how can you predict this thing? That if the ray is parallel to the base, remember this thing. Okay. So the question में क्या है? It is a question for you. You have to solve it now. It says angle of the prism here is given as 60 degree. इसको 60 degree दिया है. Okay. And they say like this, that refractive index of the glassy material is 3 by 2. ठीक? Next thing they are saying is this, what is the angle of incidence I to get the minimum deviation? Okay? They're asking you to find that minimum deviation also, assuming the surrounding medium to be air. That is N1 here, N1 here. Find the answer, students. Find the answer. So now it's required for you to find the answer. I'm giving you 2 minutes to solve this question. Then I'll give you the solution here. Okay? See, one formula is common. We know the angle of minimum deviation is given by refractive index minus angle of prism. Okay? So from here, you'll get the angle of minimum deviation. Once you get the angle of minimum deviation, then your job is to find angle of incidence which generated that minimum angle of deviation. How you can find them? Simple. Then you will use this thing. R1 is equals to R2, we know. So we'll write A equals to, because see, if you see this triangle, if you watch, focus this triangle, external angles ka sum is equals to internal angle on the opposite side, or sum of the external opposite angles, that is R1 plus R2 is equals to this A angle. This we studied in that properties of mathematics. See, there are many properties of mathematics, geometrical properties. So in that, if you study mathematical operations, I mean the properties there. So this is one of the low kind of thing. This holds there because if you study, you'll get it simple. Okay. So according to that property, I made this thing. Again, due to the angle of minimum deviation, R1 is equals to R2. So you'll get here a value like, suppose I'm taking this as common value because they are both same. So it will be 2R. So angle of prism by 2, I'll get R here. Okay, very good. So you got the angle of deviation. So Sneha got the angle of deviation as 30 degree by solving. Cool. So see, once you get R value, which is nothing but A by 2, and same here A by 2. Okay. So can't you apply here Snell's law? Here we'll apply the Snell's law. Okay. So I am showing this. Okay. So I'm showing you the solution because I hope that you're able to solve up to this only. This is for minimum deviation, we know this is the thing. Then there's also we know that 2R is A by 2. Again, it comes as, so R1 value comes out to be 30 degree. R2 is same here. Applying Snell's law at the first surface. So I will say here N1 sine of I is equals to N2 sine of R. I mean, R is what? R is this, R1, R2, same. Okay. Here also we have seen. And N2 is what? Of the glass, that is 3 by 2. N1 is of the air, you know this thing. Sine I is what? It means incidence angle, that we need to find. This is our question here. So applying this, the answer comes out to be sine I is this equals to 3 by 4. So I value comes out to be this in front of you. Okay. I'm highlighting this note, this solution in your notebook. It's important because it contains two variables. I mean, you need the angle of deviation from one equation, then you need the angle of incidence, which produced that minimum angle of deviation. Please note it down. I'm giving you 2 minutes for this. And then you have to put a text in the chat box, sir, proceed for the next slide. Okay. Till then, I'm waiting. Please solve, please write this solution in the notebooks. It's an important question. Okay, Sneha, so you have texted here to proceed next. What about other students? Have you written? Jinvi Malhar, Barsha, Anshu, please write all these things and reply in the chat box, because one of your friend have like already written the solution on the notebook. So I want your replies also. Okay, students, so that's good. Okay, I mean, you all have replied here. Okay, yeah, voice is okay. So padhao na. Okay, so who is this padhao na saying? Okay, you. No, no, I was just waiting for your replies. Okay, so that's cleared now. That's cool. Okay, so let us proceed. We got all our answers. Okay, fine. Students, this is also one kind of trick here if you see properly. I mean, we know, just hold on. We know this formula. And we did some simplifications on this, applied some laws. Then we got this formula that is this DM wala. It's going like this one. Hai. But if we see this, we know for the minimum angle of deviation, I is equals to E. So 2I minus E. From this, we get the DM like this, angle of minimum deviation from here also. And we have already found it by this formula also. This both will be same, students. Okay. Chalo, up dispersion. Chalo, now let us start the dispersion. Okay, cool. So many students have joined. Very good. So now let us start the dispersion. Dekho, I already told you the dispersion in that prism wala thing. Okay. So dispersion, you can see here, it's what spreading of white light, white sunlight, you can call, if you keep a prism in front of that, into its full spectrum of wavelength. You know this thing, है ना? हमने देख लिया ये. Let us talk about the mathematics of the dispersion. Okay, tell me, in the previous class, this was not completed, no? Reply in the chat box. In the previous class, this was not completed, no? Anyone, Sneha, reply fast. You are the fastest replier here. So that saves our time. Sabka time it saves. Please reply in the chat box. This was not completed, no? Okay, good. Okay, very good. Thank you. So see what is happening here. This is a source of light. Okay, I launch the video now. Focus here. I launch the video. Watch carefully. So as I'm increasing its wavelength from violet to the red, red, you can see how this emergent ray is deviating. It's coming towards the normal. Okay, if I bring a white light, so now white light, you can see dispersion pattern is shown. Okay, so from this dispersion pattern, you can conclude this thing ki red, if I draw normal here, so normal will be looking how? This is the line. Normal will be somewhat like this. This will be the normal. So you can see red is making the angle of deviation del r with the normal, and violet is making the angle, violet is making the angle which is this, a big angle with the normal. है ना? What we will say, let me use the red color for that. Del is making this angle of deviation. Sorry, emergent. It's which angle, students? We will not call it a deviation angle. It will call it emergent angle. Okay. Let me erase all. So if I draw normal, let us first draw the normal to this. Normal will be like this. This will be the normal. So this will be the emergent angle. Okay. This will be the emergent angle for violet. So violet color emergent angle I have drawn with the E violet. Red color emergent angle I have drawn with the E red. Okay. So now you see here that we can see here कि violet का emergent angle, violet color का emergent angle is greater than the red color emergent angle. है ना? So what we can conclude like this, that we can say now that if we increase the wavelength, because we know red is having the highest wavelength. So as we increase the wavelength, students, what happens? As we increase the wavelength, emergent angle decreases. So you can see violet is having more emergent angle, blue less, yellow less, red smallest. है ना? So with the increase, so we can see wavelength is inversely proportional to the emergent angle. A pattern kind of. See, don't take it a lot like we make the equation and try to solve the numericals. No, it's just a relation, mathematical interpretation of our whatever we have concluded here. Iska mathematical interpretation is this, that if you increase the lambda, emergent angle will decrease. And we know in the spectrum, visible spectrum, red is having the highest wavelength magnitude. इसका wavelength सबसे बड़ा होता है, and starting from the violet, and frequency is inversely proportional. Frequency इसका सबसे max होता है. ठीक है? Again, I'm launching a video last time for you. See, as I've increased, this is blue light. Now it will become, as I'm increasing the wavelength, corresponding color is coming in the emergent ray. See, red is more near to the normal now. So you can see. है ना? And now you see, again, same thing. Fine? I hope you got this thing. है ना? Fine. So now students will be seeing the mathematics or mathematical formulas connected with this, or we'll see the mathematical calculation for this experiment. There was some equation known as Cauchy's equation, which shows you this pattern, that a refractive index is inversely proportional to lambda square. What does it mean? It means like this. If you just increase lambda slowly, small only, है ना? So increment in the refractive index will be, I mean, it will not increase because it's inversely. So it will be decreasing with a very good amount. Okay, students? See next. It shows you here lambda of the violet and lambda of the red. Lambda of the red is more than the lambda of the violet. This we know. So due to this, we'll say here refractive index, because it will follow this law now. Remember this law. So according to that equation, violet ka refractive index will be greater than the red ke liye, hai na? So due to this, if I apply this minimum angle deviation condition, I'll say कि minimum angle for the violet will be greater than minimum angle for the violet will be greater than the red, minimum angle of deviation. And you can check this thing. How? Suppose, see, this is the incident direction and violet ka will be like this. So this is the angle of deviation for violet. If I see the red red will be extended. I have to make a rough diagram. Red will be extended like this back. So for this, the angle of deviation is less. Okay. Also, via this mathematical equation, you can see angle of deviation is greater than for the violet. Okay. So this video is shown you already. Write this thing in your notebooks. Only the mathematical interpretation. It's enough. And rest this thing also you can write. And reply me in the chat box to proceed next whenever you want. Okay. I'm waiting for your. Write it in the notebooks fast. Today we'll try to complete it. Written. Okay. Cool. So done, sir. Okay. Very good, Stan. So now let us move towards the natural this thing. Natural phenomenon what is happening in this video? Focus carefully, okay? I'm launching it again. When the sunlight passes through this water droplets, it is shown. Okay. Okay, I'm launching it. Okay, so now it's audible. Okay, please be focused. Okay, na? Please be focused here. So what I was saying is this: I have launched this video several times. Okay, and don't use this zoom here in between. Okay, so I'm launching this video again. See carefully. So as in the rainy season, why are you able to see this rainbow? Because when your back is to the sun, the water droplets in the atmosphere, these are behaving like the prisms. And when the white light is entering from them, it shows like water. If the water droplet is prism and the white light enters, it will show 7 colors. That's why you're able to see a picture of it. Okay. So this was all about. See, now let us see the scattering. Scattering is what? Suppose the incident light. This is what incident light like this. So when light strikes a molecule like this here, okay. So it will show what scattering. Scattering is what? When a light, see light coming from the sun or wherever, when it strikes the dust particles, you will see scattering. I mean, light goes in the different directions. It shows the pattern like this. So the definition is in front of you. When a light waves passes through an imperfect medium, then it gets deflected off its straight path and scatters in many directions. Okay. Next thing is this. Yeah. So if someone is asking from you, how are you able to see this blue color and the sky is blue color? What is happening? And is there any connection? So you can now apply the law of scattering here. Okay. Okay. Let me explain you that. Okay. Suppose we are having a particle which is having less lambda. So scattering mathematics says like this. There is something which is known as Rayleigh scattering. I mean scattering of the light. Scattering of the light. So it gives like this. The light which is having more lambda will be scattered the least. Light is which is having more lambda will be scattered least. And the light which is having the least lambda will be scattered the most. Light which is having least lambda will be scattered least, and the light which is having most lambda will be scattered the most. Okay. So if you see this electromagnetic spectra, this is the violet color. This is what the red color here. Okay. So what happens? As per this mathematics, we can conclude lambda is less. It means most scattering. So it's written here scatters the most. Okay. And red, the least, the longest wavelength, most wavelength, scattered the least. It's least scattered. So that's why, you're able to see this blue color. Okay. I mean, in the sky, if you see the waters color, the reason is this because the bluish color will be scattered the most by the particles. Visibility of violet is less than blue. है ना? See, okay, let us talk about this scene. This is something like sunset. Just focus here. You'll get the both the concepts. Sunset. It's somewhat orangish and reddish color we are able to see around it. What's the reason? The reason is this. See, suppose reason is this. That of this is we, the observer. Okay, this is we as observer. This is who? Okay, so you people have joined here, no? Fine. So this is we as observer standing here. So I am standing here, you can see. Suppose when the sun is direct overhead, so the rays will come from the sun like this. Okay. And this is the gap between the atmosphere and you as an observer on the land, on the earth. Okay. And this is made up of different layers of atmosphere. You can call as different refractive indexes. Okay. So that's why, you can see here light is entering. Let me show you. You can see here, students, the light which is entering, okay, the distance of the atmosphere through which the sunlight travels in atmosphere is this much here, is only this much. Okay, that's why you're able to see this violet color. Okay, and when the sun is near the origin, say sunset picture, this is a sunset scene, and we are able to see the red colors around it. What's the reason? That the light which is entering when the sun is at the origin, you can see when it enters into our eyes or it reaches us, it travels this much distance in the atmosphere. It is traveling this much distance in the atmosphere, students, this much distance. Okay. And if you compare that overhead scene, overhead picture, in the overhead, students, it is only traveling this much. Okay. So since light takes a lot distance traveled here is more as compared to overhead conditions. Okay. So we'll say that's why red is scattered because it is traveling more distance. Yeah, very good, Sneha. So we'll say red is scattered the. Hold on. Red is not scattered the most. See if you focus back. Let's go back on the back slide. We have seen here violet is scattered most, lambda is least, red is scattered least. But here if we see scattering of light, what is happening here? That when the sunset, why it's like this? Because when the wavelength is more, I mean it travels a more distance. No, violet light ka wavelength is less, and when sun is at the origin, its wavelength is long. Okay, I mean the thing which is, see, you people might be seen when we are in the train, when we are the train. So in front of the train, there is always a red light. I mean, so if you want to give the signal, they always use the red light. Why? Because a red light is having more wavelength. More wavelength, matlab we can see it. I hope you understood this thing. So that same concept you can use here. That's why during the sunset, okay, these waves can travel via longer distances, wavelengths discuss greater. That's why we're able to see it properly. Okay. So next is this. The summary of this, that is angle of deviation. We have studied a simple formula for the angle of deviation is this. Angle of minimum deviation is this given by this formula, mu minus 1 into angle of prism. And this is the angle of deviation. The violet is greater than the red. Okay. This we have found it. Now let us see the optical instruments first. So are you ready for the instruments? So now let us see the optical instruments. Reply in the chat box. We are having few minutes to start the optical instruments now. Are you ready with this? Reply in the chat box. Reply in the chat box. Are you ready with the optical instruments? Okay, very good. So see, first we'll go image formation by microscope. We'll see this. Then we'll see magnification by microscope. Then we'll see image formation by microscope. Then magnification by astronomical. Okay. So first of all, simple scope. See, what is this microscope? We say, what is this microscope? See, microscope is an optical instrument used to increase the visual angle of objects which are too small to be seen by the naked eyes. Okay. So let us proceed next. See, this is microscope. So there are two types of microscope we are having. Simple microscope and next is this compound microscope. Simple, this is also available in our geometry box. When we were small, we used to burn the papers or dry leaves with this. Compound microscope is, you can find this in the bio lab. We see basically different structures, the leaf in this and all. So there are, now the next slide will be this, that what kind of lenses are used here. Okay. What kind of lenses are being used in this simple and the compound microscope, that we'll see now. See, a simple magnifier or microscope is a converging lens of small focal length. Okay. Now, if you see this, I'll say like this, in a simple microscope, you use only one lens that is converging. You can call it as biconvex lens. You can call it as like biconvex lens. And the lens is held near the object. Okay. So see what is happening here. This is the complete picture. I mean, suppose this is the height of the object. This is the height of the object. Okay. And when the rays are passing from this object like this and when extended back, this will give you the height of the image. This will give you the height of the image. This is the height of the object. This will give you the height of the image. You can see here the height of the image is greater than the height of the object. And students, it follows what? It follows the microscope concept, that is microscope. We use what? To see, try this letter to see very big letters. And we are able to see very big letters, है? Is it clear? So there's a thing, we use the magnifier for magnifying. Now let us see a new concept, that is the near point. What is this near point? So it is defined like this, that it is the closest distance in front of the eye that a person is capable of focusing light on the retina. So I'm showing you the picture. See this. This is our eye. You know it's what? It's a human eye. This is a human eye. What is defined? See, if you see this green light, it's able to focus the image properly here. But if you see this black light, it's coming. I mean, if you keep the object somewhat near the nearest distance where it will be able to focus the image, that is known as near point here. So see, the closest distance in front of the eye that a person is capable of focusing the light on the retina. So if you keep your candle here or somewhat here, okay, it will not able to form the image properly. So that's the problem. So that minimum distance, that point, near point. A simple explanation up to, okay, that is the near point. If you decrease more distance, you will not able to see the object now. Okay? This we have seen. So remember this point also, that near point of a normal person is about 25 centimeters. Okay, that's why it makes hard to focus object closer to your eyes than that. So if you keep an object, suppose you're eating an apple, not an apple, apple is a big object. That is also difficult to focus. Okay, if you're seeing something, okay, and if you keep it, suppose these are our eyes, and you keep an object at this point, this will be difficult. If you keep it more closer, you'll not able to observe, focus it carefully. You'll see a blurred image. You'll see a blurred image. Okay, I hope it's clear. You'll see what? You'll see a blurred image there. Now let us move next. So we'll see a little bit about this angular magnification by microscope. What does it mean? Suppose this is your eye, and suppose this is a ray coming. Suppose this is the height of the object from your eye, the distance is d of the object. Okay, so, and suppose this is the object tip and your eye is here. Distance of the object from you is this. This you'll call as a near point. This will 10 alpha will be h upon minus d, because according to sin beta will be what? ये image के लिए. If the image is somewhat, say, yeah, see this. The image is this. Iska angle is what? Beta. So beta will be what? H dash upon the distance total from the eye. It is here equals to minus v. So now what we'll do, we'll define angular magnification. So angular magnification, students, is defined as beta upon alpha. Suppose students 10 alpha. See, if I say like this, alpha is very approximated, very small. So I will say 10 alpha can be approximated as alpha. If I say beta is very small, so I can approximate 10 beta as approximately equals to beta. So I'll approximate these things. And I will define angular magnification, which is a formula you need to remember. It is defined as beta by alpha. What does it mean? It means h by minus u, okay, upon h by minus d here. This will be equals to minus d by h. That is d by u, angular magnification. This is the near point. This is u is the distance of the object from the lens. Is this thing clear, students? So we can end them. Okay, these all things are defined. Is it clear? Angular magnification is clear, students? Okay. So see, simplifying. Two lenses are there, no? Simple microscope and compound. So when the object is at infinite, so rays will be coming like this. Hai? So for this, we know actually angular magnification is what? It's d by u. But if the object is at infinite, okay, I mean, you will say like this, you will keep u equals to focus. Okay. So you'll get magnification as this. Oh, sorry, when the image is at infinite, I'm sorry. It means the elongated image, we don't know its height is like infinite because it is at infinite. Okay. For such case, I'll keep object to be at focus because you know this thing. If you keep an object at the focus of the biconvex lens, images will be formed as infinite. Okay. So this is the condition of magnification there. And case second is this. Suppose when the image is at near point, that is, if you keep v equals to d, so you'll use this formula. You'll keep here v equals to d with sign and convention. You'll put it as minus d. This is h. So you will get 1 by u. You will get 1 by u as this. So from this you can extract magnification as this. Okay. So this is the formula in front of you, that when the image is at near point, you will say what magnification is this. And when the image is at infinite, you will say magnification is this. Okay. Both the formulas I have kept on your screen here. This is for near point. And when the image is at infinite, magnification is d by f. Remember this thing. So we can say these are the two formulas for image at infinite, image at near point. But these are images, not object placed. Okay. Near point, image, both for the image. From this, we can conclude magnification is defined as 1 by f. So a simple microscope, we can say like this now. A simple microscope has limited magnification for particular focal length. Okay, remember this thing. So students, this was all about today's class. Fine. Okay. This was all about today's class. There was a network issue. I'm sorry for that. Okay, maybe, sometime it happens, the network goes sudden. So in the next class, we'll see compound microscope. But remember one thing, let us do some conclusion. So we started with the prism. We have solved two numericals. Okay, one was very simple, direct formula based on this, that is mu minus 1 into angle of prism. Next, we found the angle of deviation, but now they were asking incidence angle. So we used this formula, this trick, that is R1 plus R2 equals to A. We founded R1, then we used the Snell's law, then we find an I angle, which produce this minimum angle of deviation. Then we seen dispersion. We have seen scattering somewhat, which is just a little bit of the theory required. Then we proceeded towards the lens, this optical instruments. Okay. Is it fine, students? So next class, compound microscope and telescope fast, and then wave optics chapter, new chapter will start. That is our favorite chapter, wave optics. In the next class, we'll start this chapter. Rest of the things are very easy. A compound microscope is remaining, telescope remaining, astronomical, and all this, some factors related to that. This will be ended soon in 25 minutes. Okay. So that was all about today's class, students. Thank you. So we'll meet in the next class. Before that, I'm starting an NPS here. Please participate in this. Please, students, participate in NPS, and then you can leave. Okay. Okay. Bye, all the students. Neha. Bye, everyone. Please participate in this NPS, and then you can leave. Okay. Only 20 minutes thing is remaining in the next class. We will start directly wave optics. Bye bye everyone. Take care. Study well. Be happy. We'll meet in the next class. Till then, you can enjoy your days, but don't forget, like, don't waste all the time in enjoyment only. You must study. Okay. So next week, maybe we'll start. You know? Cool. Participate, all of you there. Participate here. Bye bye everyone. Bye everyone. So how many students are there? Let me see. Okay, so these are. Bye Ankita, bye Anshu, bye Sandhya, bye Subhalakshmi, so all JNV students. Bye everyone. Okay. If you're having any doubt, you can reply in the chat box. Otherwise, you can leave. Goodbye, Barsha. Bye everyone. Bye JNV Khurda. Okay, I'm ending this now. Participate fast, students. Who haven't participated, participate fast. Remaining students participate in this. So I can end the class now.